Now let us have a look at the general properties of this scattering matrix. So this can actually be defined in very general contexts, including beyond one-dimensional problems, but let us focus on one-dimensional settings. And the setting is that we have two regions where the particle can move freely, and in between we have a region where the potential can be really anything. This we call the scattering region. So here we have so-called incoming amplitudes A1 and B2 and outgoing amplitudes B1 and A2. And the scattering matrix is simply expressing the outgoing amplitudes in terms of the incoming amplitudes. So the ones which stipulate where the particle is coming from. And then we find for these one-dimensional problems that the scattering matrix is always symmetric and indeed also always unitary. And this is evaluated all at non-negative real energies where the particle can really move. But if you evaluate the scattering matrix at possibly negative energies, and you find that it is infinite, so it diverges, then you can find also the bound states. Now these are three key properties of the scattering matrix in one-dimensional settings, but this can also be generalized to more complicated situations in which the scattering matrix then becomes a larger dimensional matrix. So instead of just a 2x2 matrix, it has many more entries. And then we will find the following generalizations. Namely that the scattering matrix will always remain to be a unitary matrix, and that it also still diverges at the energies of the bound states, including one can also then find so-called resonance solutions, where you take an energy which is no longer real, but complex, and this actually corresponds to solutions with a finite lifetime. So the particle will be trapped in a certain region for a finite time. Now this is certainly a little bit more complicated, but I just mention it here for information. And this property here will not always be true, but it will distinguish two different classes of physical systems. Namely, this is true, I give you first a technical term, if the system obeys time reversal symmetry. Now this is a symmetry between the particles moving forward and backwards in time, and they relate simply these amplitudes here. Now in which cases can this be violated? Well, the most important case is that of a particle moving in 3 dimensions in presence of also a magnetic field. So this condition that the time reversal symmetry is true in that case would be that the magnetic field vanishes throughout all space. But if the magnetic field is there and it is finite, then time reversal symmetry is actually broken. You see that already classically, because classically a particle would now experience a Lorentz force, and if you send it back, it will not just retrace its step, but it will just continue this so-called cyclotron motion in the magnetic field. And this is different from the propagation without a magnetic field along a straight line, where you can simply send the particle back. So this is for a finite magnetic field. And this is a situation where the magnetic field vanishes. And as it turns out, this property here still remains true if you include a normal potential V. So this is allowed. You still have time reversal symmetry in this case. One can verify this property by looking at the Schrödinger equation, but for this we have to look at it in 3 dimensions, and we have to include the magnetic field, which is described by a vector potential. So the 3-dimensional case with the normal potential energy we will look at very soon, but the case of a magnetic field we will only cover very much later in this course, so I just mentioned this here for completeness. Now it is very instructive to look at the following situation, that you have 2 different scattering regions just placed in series. So now we have 3 regions of free propagation, And in there we can introduce amplitudes A1 and B1, A2 and B2, A3 and B3 for the particle moving either to the right or to the left. And for both of these scattering regions, we can introduce a scattering matrix S1 and S2, and we can now simply ask the question, what is the scattering matrix for this composed situation? So what is the scattering matrix which is relating these incoming amplitudes to these outgoing amplitudes? And this we can obtain by writing down the scattering conditions from the definition of the scattering matrix and then eliminate these amplitudes. Now the algebra is very similar to what we did when we worked out the transmission probability through the barrier, where we also eliminated two coefficients in the middle of the problem. So I'm just going to give you the key result, which is the reflection probability expressed in terms of the reflection probabilities of these individual scattering regions. So this is just the exact algebraic solution of this problem, but it can be rewritten in a very instructive way. And for this we are going to rewrite this fraction here as a geometric series. Just like this, involving all these powers of these reflection coefficients from the different regions. And if we insert this here, we obtain that this reflection probability can be also expressed in the following way. So I'm just going to collect all the terms, starting from n equal to 0 here. So this one will just be 1 in that case, for n equal to 0. And that will now appear at this place. So we simply obtain T1 prime R2 T1. And this is just the very first term of this expansion here. In the next term, we just have extra factors of R2, R1 prime arising from these powers here. So this will look like this. And so forth. And so now what is the physical interpretation of this? Well, we can interpret this as different processes that are interfering with each other. First of all, we have this coefficient here. This describes the reflection from the first scattering region. So this process here. Next, we have this process. Note that we are always going to multiply these amplitudes from the right. So first of all, we encounter a multiplication with T1, and this is simply the process of transmission through the first region. Then we encounter a reflection from the second region. And then we encounter again a transmission through this region here. This is just the coefficient T1 prime. So this is clearly a second process by which the particle can return to where it was coming from. Now let's look at this term here. There we first again transmit through the first region, then we get reflected from the second region, and now we get reflected once more from this region here. So we return here, have another reflection process there, and then finally we end up again where we were coming from. So we have some additional scattering processes in the interior of the region, so sort of closed loops. And indeed we can have these closed loops of scattering multiple times. So here we simply have one additional loop of this kind. And this then simply carries on. So at the end we end up with the sum over all the different ways for the particle to return to the original position. Note that these are amplitudes, so we add up all these amplitudes and not the intensities, which will correspond to the probabilities. And this really shows you that we are dealing with wave effects also in this case. Now, a very characteristic phenomenon of waves are resonances, and we can now immediately see where they come from. For this, let us assume that we have some constructive interference in these internal loops. So this means that when we start at this point here and we scatter back to this point, we want to have the same amplitude as we had before. This simply means that this following product needs to be 1. But in the reflection amplitude, exactly this combination appears in the denominator. So this would lead to a diverging reflection amplitude. Now the reflection amplitude cannot diverge. Indeed, the reflection probability, of course, cannot be larger than 1, but this simply means that R can become relatively large compared to other situations, in particular as a function of energy. So the energy of the particles that arrive to this region. And what this means is that if you look at the reflection probability, this would lead to a situation where the reflection probability is very small and then it suddenly becomes very large, close to these resonances. Now the same can also happen in transmission. So this would then simply apply to T, or if you consider this in terms of the reflection probability, then the reflection probability would just drop to a very small value at this particular point. These are so-called reflection or transmission resonances. These resonances are of course a very general wave phenomenon. They are basically the same kind of resonances that you're familiar with from musical instruments. But in this quantum mechanical setting, we can study them in great many detail. Finally, let me mention a real-world application, and this is known as conductance quantization. Now, this actually applies to a setting which is close to but not exactly one-dimensional. So I'm going to use some slightly generalized notions, but this is really just for information because it's just a fascinating phenomenon. In there you consider a so-called quantum wire, which is an essentially one-dimensional wire for electrons, but at very small dimensions so that the electrons behave quantum mechanically. So this has a very small diameter d, but this diameter does not exactly vanish, which is the reason that this problem is not exactly one-dimensional. Indeed, what you find is that you can treat this problem in this direction as a particle in a box, and so you find different numbers of solutions at different energies. And this will translate into different ways for electrons to propagate into this direction, and these different ways are called channels. So let us assume that there is a fixed number of these, and let's call this n. Now we also place another wire on the other side, and this has the same number of channels n. The scattering matrix will now be made out of not just numbers, but matrices themselves. But each of these are simply n by n matrices. And please don't worry about the details, this is not the essential part in here. What one can then do is to carry out an experiment in a system which has a constriction in the middle. So this constriction has a smaller diameter, and let us assume that this corresponds to m channels. A smaller number of channels because this diameter here is smaller. Indeed, all of these numbers of channels depend on the energy of the system, because you can simply access higher excited states of the particle in the box when you increase the energy. And now one can apply a voltage to drive a current through the system. So we would say that we have a source of electron on one side and a drain of electrons on the other side, and we can then measure the conductance of the system. And what you then find experimentally is the following result. So now this would be the conductance as a function of energy, or practically as a function of voltage, because the voltage is a way to elevate the energy of the electrons. And then you find that there are very well defined steps in here. And now the positions of these steps simply correspond to the energies where the number of channels increases by 1. Furthermore, the height of the channels has a very particular value. This comes out as 2 times e squared divided by h, a number which is known as the conductance quantum. This involves fundamental constants, E and the Planck's constant. So this is h bar times 2 pi, so the original Planck's constant as Planck introduced in the context of black body radiation. And a factor of 2, which is actually related to the spin of the electron, because there are simply 2 different types of electrons, as we will learn later, but this is just a detail. What is important is that this is simply related to the fact that at these different energies, the number of channels changes, and therefore there are more ways for the electron to propagate from one direction to the other. And indeed, the conductance itself can be expressed in the following way, as 2e squared divided by h, so this conductance quantum here, and then the trace of t dagger t. So this is the trace of this matrix complex conjugate and transpose multiplied by the matrix itself. Now here we just have the product of 2 matrices, and the trace tells us to take the result and just add up all the values along the diagonal. And if you do this, you just obtain the following expression, namely the sum of all these amplitudes squared. So these can be interpreted as probabilities, namely all possible ways to travel from these channels into these channels on the other side. Now if you just work this out for such a constriction at an energy or voltage in one of these plateaus, you simply find that the electrons can move mostly freely through this constriction. So there are m ways to travel through this constriction with a probability very close to 1. And so all of these add up to m. And only when you get 2 energies where the number of channels changes, you find some deviations from this result. So you find these conductance plateaus at these values G0, 2G0, 3G0, and so forth. And this phenomenon is known as conductance quantization. Well, this formalism is very general, and this equation here is a very famous equation, which is known as the Landauer-Büttiker approach. This concludes this segment on scattering theory. So I showed you the detailed derivation of the transmission probability through the barrier. I also described a second exactly solvable situation, namely the scattering from a delta function. And when we wrote down the general solution, we found that this can be conveniently expressed in terms of the scattering matrix. And finally, we had a brief look at the most general properties of the scattering matrix, which single it out as a very useful object for calculations. So for instance, you can use different scattering regions and work out a scattering matrix for the complete region in simple algebraic steps. And the scattering matrix is indeed employed in practical applications, as I illustrated for the conductance quantization. So it is one of the tools which we can use in quantum mechanics to actually make predictions about realistic physical systems. And many of our conclusions are actually based on the general structure of these expressions. So quantum mechanics is not always about solving very complicated problems in detail, but often enough we can learn a lot by looking at the key features of simple general expressions.